Hello and welcome to the first part of the first of the tour videos. So this tour is going to be focused on pathfinding. So with pathfinding, there's a lot of steps we need to put together for this. And we're going to begin with building up what's called our path data. Path data is our representation of the world that the pathfinding system uses. It holds all the information that we need there for it being able to plan a path through the world. And our path data is a really crucial part because we have a lot of systems that build on top of it. And it's important that we get the path data right, because if we don't, what tends to happen is not that it causes errors downstream and doesn't cause, crashes, things like that. It causes incorrect behavior, which is much harder to spot and is also then potentially much harder to fix because you've built a lot of things on top of it. So we're going to take a bit of time to make sure we get the path data correct and working. That's going to be the first focus there. Now, what we're operating in is this. It's our procedurally generated world. Now, within this world, we have terrain that's able to be procedurally generated. It places items, it places some buildings that we can see here, and we're going to be using that. Now, this terrain is quite large. It's 1 kilometer by 1 kilometer with a height map resolution of 1025 by 1025. So each grid cell in this height map is a little bit under 1 meter by 1 meter. Now, with our path data, we have a lot of different formats for path data. And fundamentally, path data is nodes, which are connected by edges. What a node is can vary a lot. So in older games, what you would generally see is those nodes were an individual point, so a single point in space. So it was like the edges were tightropes connecting the nodes, which were posts that you could stand on. So that was called a spatial graph. What we often see these days is something called a navigation mesh. With a navigation mesh, our node is a polygon. Might be a triangle, might be a square, could be higher order than that. We also get navigation volumes for if something can move in all 3 axes, where with that, your node might be a cube. So we're going to be using a navigation mesh. We're sticking with things that are constrained to the ground. We also, with that, we're going to use a regular grid. A regular grid I find for open environments like this tends to work quite well. If I was doing a more built-up environment with a lot of buildings, things like that, then using triangles would be, I think, a more efficient approach in that case. For this, using grids is going to work quite effectively for our setup that we've got here. So we're going to be using grid cells with there being cubes, being squares, and we're going to build it up from that. Now, if we take a look at some stuff we've already got set up. So one of the things I did was for the procgen, it actually outputs 2 textures. And one texture is a map of the biomes. The other texture is a map of the slope. It's actually a map of where it uses the y component of the normal, which is why areas that are very flat are nearly white and areas that are nearly vertical are more towards being black. So that's why we've got that information there. So we're going to be able to use that in our path data. I've also set up a little bit of infrastructure for our path data manager. So it has this concept of path data sets, which we want to be able to build multiple sets of path data. A set has a resolution. So that allows us to say, okay, well, our current map is where each cell is slightly under 1 meter. But if we had a really large moving object, it doesn't need that fine a resolution. We can go much smaller. So this allows us to, if we need to, generate coarser versions. Initially, and our focus for today is just going to be having a one-to-one mapping, because there's a bunch of things we need to make sure we have working perfectly before we introduce that added complexity of, and now we're combining cells into larger cells. So we're going to focus on just one by one to begin with. But we can have multiple of these sets. And you'll notice it only shows the resolution there. And that's because I've set up a property drawer that only draws resolution. It's not drawing any of the other stuff connected to it. That's something where we might actually end up changing how we're working with that, because we do have a slope limit as well, and we'll see what we end up needing for that. But for now, we'll just keep it that it's only drawing a very limited amount. The path data itself is currently a scriptable object. That's intentional, so that we don't have the data being stored within the level. Because if we have the data stored within the scene, our path data can get quite large, and that's one of the initial things we're actually going to focus on, is the impact there with the size of the path data. So our path data is a scriptable object that's held within one of these sets, and we've already got some stuff set up for some basic infrastructure for if we need to draw gizmos, which we will, and some infrastructure here for setting up the path data. So we're actually creating that scriptable object procedurally, and we're saving that asset out. We've got a few little bits and pieces here that we're doing just to handle the scenario of, okay, well, this could be running at editor time or it could be running at runtime. So I want to try and keep it that it can support both. So we've got our little bits of editor wrapping here for this that we need. So we're going to dive on in. And what we're going to start with is the size of that path data. And it seems like that might be a strange thing of getting the size of that path data right and getting our nodes set up. But we have a map that is 1025 by 1025. That means there's more than 1 million nodes. That means whatever our size of our node is, that is going to increase rapidly the size of our actual asset. So we're going to get this initially set up where it's creating that asset and sizing it, and then we'll go from there to see how that looks in terms of the space and everything, and if there's changes we need to make. So first thing we're going to set up is system serializable public class path data node, and it's going to need a few things. So it's going to need a world position. So we'll set up our world position. Rename that. It's going to need its location in the grid. And I want to store the location in the grid because this is actually going to allow us to achieve a bunch of really key optimizations. So having this will be really handy. So I'm going to have this grid pos. Well, I have set up conveniently a couple of things here in terms of nodes are going to be able to have attributes. So we're going to have that as something. That allows us to store some extra information there in the node of, is it walkable? Is it at the boundary of the map? Different little bits like that are going to be really helpful. I'm also going to store each node, rather than actually generating the edges and storing them as separate data. Because we're on a regular grid, we can very cheaply look up a node, and in particular look up a neighbor based on its location. So I just need to know if a neighbor exists, and I can very quickly look it up. It's going to save us on having a lot of extra data that we need to set up. And that is something that there's always a bit of a balance with path data, is that trade-off between performance and the actual physical amount of memory or disk space that's used. So it's a constant trade-off, and there are some areas where we want to make some gains to balance out other areas where we need a bit more storage or a bit more performance. So in this case, I'm using a little bit of storage, but it will allow me to avoid a larger amount of storage, even though it makes the querying operations a little bit more complex, but not problematically so. So neighbors. So, okay, well, I'm going to have in here, I need to be able to store all of these particular nodes. So, okay, let's set up. Now, our path data isn't going to be changing at runtime. So I could have path data node nodes. Then I'm going to need a way to initialize this, because I don't have a constructor being a scriptable object. So to initialize it, I need to know my dimensions. So vector to int dimensions. I'm going to want to cache that. That's definitely information that I want to make sure I'm storing. Dimensions. So we'll store that. Dimensions is equal to that. And we'll also make sure that we're storing that resolution as well. I think that will be useful for us to keep track of. Any resolution. Don't know for certain if we'll need it, but it's something where it's not taking up too much space, so I think it's worth tracking. Then our nodes is equal to a new Pathdata node, and we can give it the actual size. So it's going to be dimensions.x by dimensions.y. So there we go. We've got our new set of the Pathdata nodes. Now, at this stage, if we go and create this and we go and run it, we need to down here initialize this Pathdata. So what I'm going to do, and this is actually something with that allocation, that's fine there. What I will do is we've got our source terrain. We can access the terrain data, the height map resolution. So this is our scale. This is our Pathdata resolution. Pathdata size. So we can then do Pathdata initialize, and we give it the resolution, which we have from our Pathdata set. So Pathdata set resolution, and a new vector2 int, Pathdata size, Pathdata size. Now if we just run that, not too much is going to happen. We should expect to see our asset created. So we'll run it. It should run pretty quickly. It takes a little bit because it's got to save the asset, but we've run. So we'll have our asset here. And what I just want to check is, because one of the things we're going to be keeping an eye on is the size of this. Now, at this stage, the size of it, we can see already. It's large. And if we take a look at that asset, not that we would normally directly view the text for an asset, but if we take a look at this, be able to see why. So this is down to how Unity serializes these. These all get stored out as separate ones. So there is a lot of extra text here for saving these out. It's a lot of extra data and information as a result. So what we're going to do is we're actually going to do an initial thing here where we do a little bit of optimization for this. And our Pathdata node, we're actually not going to serialize that. That won't be serialized. We're going to have a separate set of data for what we serialize, which what we're going to do there is this won't be public. This will be data that we keep hidden, but we will be able to serialize this. So it won't be visible to people in part because I've done a custom inspector that makes it so that nothing is shown. So I'll have a serialize field. We're not making this public. We only want to have this be internal. So this is going to be E Pathdata node attributes as an array. We're going to have serialize field, neighbor flags as an array. And then what we're going to do is we're going to hook in to Unity's serialization, because we can get a serialization callback. And we'll see there are two specific functions we have to implement here. So we have public on after deserialize and on before serialize. So what we have to do with these, if we look at the description for them, onAfter deserialize will run after it has deserialized our object. So after it has loaded these, but before it's then processed other stuff. And I'm actually even going to specifically, not that I need to, but mark that as not serialized. So we've got our serialized data. I'm going to actually just convert all of these other ones over to being serialized field for consistency. So nodes is not going to be serialized. We're going to have to pull stuff into this. So onAfter deserialize, it will have loaded our, if we take a look again at the descriptions here, it will have run after it is loaded this data. So it'll have loaded that data. And so we'll be able to pull that data into our actual nodes. So what it will mean is when I initialize here, I will create nodes. And then after it's loaded, it's going to need to initialize this. It will have dimensions. And then what I will do is I will pull the data in to that. So it'll be a case of for int index is equal to 0. Index is less than, and it will be attributes dot length index, and then I'm going to go through this and it will be node at index attributes is equal to attributes at index, and then I will also transfer the neighbor data. So we will set the neighbor flags. So initialize the nodes. And then I'll actually do the reverse here for generating the other data. Extract data from the nodes. So in this case, what I would do here is attributes gets initialized based upon nodes.length. And I'll actually use attributes.length here as well. And we also do the same with node flags, or the neighbor flags, neighbor flags. So although this is a little bit of extra setup and it seems like, why are we having to do this to begin with? This is because this fairly heavily changes the look of our data, and it's important that we get it right to begin with. That's good. So, okay, we're populating the attributes and the neighbor flags. We're pulling that data across, which is great. But we've got world and grid position. So these are not too difficult to grab out. We actually can calculate these. So our grid position, so our nodes index dot grid position is a new vector3 int, and we need the x, the y, and the z. So we're organizing stuff by row is the approach we'll go for. The row will be stored in y. So that means that x is going to be our index modulus with our dimensions dot x, so the width in that direction. So x, y, and z will just be 0 for now. And our y ends up being index minus x divided by dimensions dot x. So, okay, that's good. We can regenerate our grid position. So now we're really cutting down the amount of data that we've got to store. And we want to keep in mind, at the moment it was 107 meg. We're wanting to get it to be much, much lower than that. So final thing is we need to be able to calculate the world position. So to do the world position, we can get that from our grid location. We absolutely can. But we need a couple of extra little bits of information to do that. So we actually need to have vector 3, and this is going to be the size of our individual cell. So cell size. And we also might need to be able to offset it, but for now we'll just have that cell size in here. So then have vector 3 cell size. So that's good. So cell size, so we're storing that. And then we'll be able to reconstruct this. We'll be able to say nodes, index, your world position is a new vector 3. It's going to be x times by cell size dot x. The y position, well, we don't have that, and we can't go from the x and the z to that. So that's going to be an interesting one, but we'll be able to get that in a moment. For now, I'm going to put that as 0. And then we'll have y times by cell size dot z. So that's good. So our heights, we can actually store those out as well. So we'll have an array of heights. And so these heights, we do the same thing here where this then ends up being heights index. Means we also need to populate our heights down here. So heights is equal to new float nodes.length, and we just pull that information out equal to nodes index world position y. What we're doing is we're extracting out the bits that we can't derive, and we are then taking all the bits and stashing them into arrays and individual arrays, which will make it a lot easier. Height map, scale, source terrain, height map scale, that we can pass through here as our cell size. Will work. So let's test with that. Now initially it's probably going to be a little grumpy because it doesn't have that data stored, which is fine, because we're going to regenerate it. And we want to just check that that regenerates clean. So we do need to address a couple little issues. So f nodes equal to null, or nodes length is equal to 0. Then what we're going to do is just do a return, but before that we'll say attributes is equal to null, neighbor flags is equal to null, and heights is equal to null. So we just wipe those out, and that should make it a little bit happier. Let's generate the data, make sure it saves okay. So still getting a couple of errors to be expected. There's a few bits we need to get up and running with this. So this is trying to pull data out of those, but these nodes are not fully initialized yet, which is okay. And that'll be because those are not actually technically allocated yet. So what I'm going to do just as a temporary thing, index is 0, index is less than nodes length. This is just to pad out the size. So nodes at index equal to a new Pathdata node. That'll just allow us to make sure we've got some data in there. Generate. So it's generated that. We'll do a save. And if we take a look at our scene file and the size now, we've gone down to 10 meg. So it's gone from 107 meg to 10. And if we take a look at why, that's because it's able to store this with a lot less junk. It's much, much more efficient. Our attributes get stored like this. So it's significantly more efficient in terms of how it's storing the data, which is good. So I know this is a bunch of setup and infrastructure for actually making the path data, but this allows us to store it efficiently, and that's really important. So now we can focus on the actual generation of it. So I'm going to set up a specific version of a function here. So I'm going to go for, because this stuff is common things, I'm going to create another build path data that actually just takes the path data asset itself. So internal build path data. So it's going to just take the path data. And that's actually the key bit that it's going to have. I will also give it the path data set. And that's going to be the configuration, I think is a reasonable term for it. So we'll do this. We've got the path data, and we've got our configuration, which is our path data set. Okay, so let's start building this. Well, we're going to need to loop over all of that path data. That's one of the key things. So we're going to go through our terrain map, that height map, row by row, column by column. So we're going to have row, and I'm intentionally using our traditional integer-based for loops here because we're doing so much of this performance. Any little gain that we can get is really important with this. So it's going to be less than path data size. Then we have by column. Column is less than path data size. Add to that. So that's good. Now we know our path data is already initialized, so that means it's pretty straightforward for us being able to directly update the data. So, okay, few things we need to set up. We need to give this node its grid position. So need to give it its grid position. So what I would be doing is I'd say, okay, path data, initialize node. I'm going to just pass in row and column. Well, we need the location for it. That node's going to want to know where it is. Row and column will be enough for it to give it its grid location. I also want to work out the attributes for it in terms of, is this underwater? Is this, walkable? Things like that. So there's a few bits of extra information I'm going to need. But first, let's get the location. So I'm going to just go for how we were calculating it before. So this is from the procgen side. So, okay, we're going to have vector3 world pos. Well, a height map scale, we can easily grab that. Going to be using that a bunch. So y, in this case, is our row, and x is our column. So that's good. We've got that. We also need the actual height map. So let's retrieve that. So var height map, source terrain, terrain data, get heights, and we just retrieve the entire height map. So, okay, we've got our world position then. So that's something we can pass in. Grid position, it'll be able to calculate. Good so far. We want the attributes as well. So attributes, which is going to start out at nothing. So we want it to be none initially. But that is something that we'll pass in here. Oops, not that. Attributes. Autocomplete's being a little too helpful. So let's set up what this initialize node function looks like. Because that's going to sit here on our path data. So this will be public void We've provided the row and the column. We've provided the world pos and our attributes. Now we need to know which node to modify. So, okay, node index is going to be column plus, and we're reversing essentially what we did here. So column plus row multiplied by dimensions dot x. Because then we can just directly go, well, nodes, node index, your world position is equal to world pos. That node's attributes are just equal to attributes. And then its grid location. So node, your grid position. Well, again, it's going to be a new vector3 int. We already established that we're using our x for the column. So this is going to be column, row, and then 0. I'm using a vector3 because there's a couple little things I'll be wanting to do at a later stage that having this as a vector3 now means that we'll know that we've got all the data there ready to go. So, okay, so far so good. So we're extracting some key info. Extract key data. Process the height map. Now, here we're generating the world pos. Build the attributes. Initialize the node. So let's look at what we want to set for these attributes. So, okay, water is if it's below a certain height. So that's straightforward. If world pos dot y is less than water height, then we'd say attributes, and we will set ePathdata attributes has water. Otherwise, it might be walkable, but we need to check the slope. So our slope, if we take a look at what we set up, we've got our angle here. Now the slope map is the y component of the normal, which means if we take the cosine of the slope limit, we can actually directly compare that, because when the normal is flat, so it's 0 degrees, its value is 1. The y component is 1. When the normal's pointing directly horizontal, so the slope is vertical, y component is 0. So cosine maps really nicely to that, because cosine of 0 is 1, cosine of 90 is 0. So we'll be able to do a comparison there. We just need to extract from the slope map. What I'm going to do, because we'll be using it a lot, is cos slope limit, mathf cos, configuration slope limit, and we'll convert that to radians. Now I need to query that slope at that particular point. So what I'm going to do is determine the slope. And the way that I can do that is I have my source slope map, and I can do get pixel by linear. So it does a little bit of filtering if we're a little bit off, which I think is good. So this is going to be texture U, texture doesn't exist yet, but that's fine. Texture V, and it'll be the red of that. Could use red, green, or blue, any of them would work. Slope. And that's actually the cos of the slope. So to get these texture U and V, well, V is going to be the row. So texture V is going to be row divided by path data size. Texture U is going to be fairly similar, where it's going to be using the column. So texture U equal to float column divided by float of path data size. So that looks good, because we can then check. So if we think about this, higher values mean it is more shallow, flatter, essentially. So if cos of the slope is greater than or equal to cos slope limit, then it is walkable. So attributes or equal walkable. Then the final thing we'll do is we want to check for if it's on the boundary. So if row is equal to 0 or column is equal to 0 or row is equal to path data size minus 1 or column is equal to path data size minus 1, then we'll say attributes equals, because we want to stomp the other ones intentionally. So we'll say that that is the boundary. So that looks pretty good. Should be populating the attributes, initializing all of that. We're not doing the neighbors yet, but that's intentional. That will set up once we've actually verified that this data is working. So I've got some gizmos set up here for being able to draw stuff. So I want to draw the nodes, but I want to only draw the nodes if they're nearby. So for int node index is equal to 0, node index is less than set dot data dot nodes length. Then we retrieve the node. So var node path data set dot data dot nodes, retrieve the particular one. And so we're going to do a check and see if it's too far away. So if node dot world pos minus camera location, I'm going to check if the square magnitude is greater than, let's make it fairly close range, so 50 times 50. Then we'll just skip it for now, just so we're not trying to draw a million lines, which would understandably be a little bit slow. We'll just do gizmos draw line node.worldpos, and we'll do node.worldpos plus vector3.up, and we'll change the color based on the attributes. So to make this a little bit easier for checking the attributes, I'm going to set up some helpers here. So is boundary, we'll just do neighbor flags, or sorry, neighbor attributes, has flag, boundary. This just makes it a quicker and easier way of querying the stuff. We don't want to have to every time write out the code for if it has the flags. That's just going to be messy. So is walkable and is water. Because what we can then do here is, okay, well, if node is boundary, I'm just going to actually not draw it, because boundary ones are there intentionally as a bit of a buffer, so a safety margin. But if node is walkable, then I'm going to set the color to green. Otherwise, if the node is water, I'm going to set the color to blue. And then finally, if it's not either of those, then it's unwalkable. So I'm going to set the color to red. So I want to just test at this point. I haven't built up the neighbor information. I just want to make sure at this stage that everything is working. And we'll have a few things where we've got some errors, just because it's going to be a little grumpy as we're adding in and configuring the data. It's a little bit to be expected. And so we'll be able to, with this, it's trying to access these nodes. I want to just check if that node is equal to null. then we just abandon as well. Technically shouldn't happen once we've got some data properly built here, but because we don't have stuff properly built, it is going to tend to happen. The other thing we need to do here is this, and this will be what we actually missed, is a new Pathdata node. It's likely why it's getting grumpy at us, because we missed actually allocating the nodes in that case. So if we clear that, we're going to generate the data. So it's run, it's generated, which is good. And then our debug, we can see we're seeing lines here. They appear to be lining up with the terrain, which is good. And that's one of the key things, is making sure stuff lines up. It's lining up with the water height there quite nicely. Now the slope limit, if we look at that, that does not appear to be working correctly, because we've got quite steep slopes here and it's not registering those. Somewhat it is, but not entirely. Okay, so we know our slope stuff seems a little off, and this is one of the things why, as I said, we really need to test stuff very carefully. There does seem to be generally working, but there's clearly some bits where it's not. And one of the most likely causes of this is actually having things swapped. So we almost certainly here, we've actually, if we rename these, we've gotten the order of these around the wrong way. And because we're mixing between so many different systems, that can really easily happen. So we'll check with this. And the other thing we noticed is when it reloaded there, we lost some data. So that's going to be another thing to look at. But now we regenerate, that's looking spot on, that's correlating, so that's good. But we did also see some weirdness when we reloaded back in. So that's likely when it's loading that asset. So if we go to an empty scene and load this back in, well, we can see we've got heights, everything like that. There's a general shape, that data is clearly there, but it's misaligned. So that means that we've actually got an error in our calculation here, in terms of we've probably got our X or our Z swapped here. This is likely going to be the case, that actually that needs to be swapped around, which I believe when we were calculating here, it was using row. So yes, that makes sense. That should mean when it reloads, it's then correctly registered, which is good. So it may not seem like it, but we've actually solved one of the key issues and the key things in getting this up and running. We have our data properly registered in that it is conforming to the terrain. The values that it has match with the sections on the terrain, and that's a really good point to be at with it. And our level file has grown a bit because we've got more data in there, but it's 20 meg as opposed to 107 meg, which the one was before. But with this now, we can build our edges. We can build up the neighbor information, which is great. So build up the neighbors. So again, we still loop through everything. That's still a key part of this. But it's going to change a little bit how we actually then process at this point. Because what we then are going to want to say is, okay, well, let's grab the node we've already created. So we're going to want to say, okay, Pathdata, get a node, and we'll give it a row and column. So we're going to have here a node, and we'll set up the get node function soon. But some nodes are forbidden from having edges. In particular, boundary nodes. So, okay, let's save some work for ourselves. If this is a boundary, do nothing. So boundary nodes do not connect. Now the next thing we need to do is we need to then get the neighbors around it. So we're going to get this get node function implemented. And we'll set this up down here. So public Pathdata node, get node, in row and column. And then first thing I want to do is check if those are valid. So if row is less than 0, or column is less than 0, or if row is greater than or equal to dimensions.y, or column is greater than or equal to dimensions.x, we return null. That's a super handy thing for us to have, because that's going to make it really easy for being able to know, is a node there? It gives us a quick way of checking, does this node at a location exist? Otherwise, we just return nodes, and we can do column plus row multiplied by dimensions.x. So that's good. We've got ability retriever node. Now we need to check our neighbors, and we've got 8 potential neighbors. So we need to have a look and retrieve those. So I'm going to write out the logic for this, and then we're going to clean it up a bit, refactor it into its own standalone function. So firstly, I want to be able to retrieve a node at a particular location. So I want to be able to say, okay, well, Pathdata, get relative node. So we need to give it the starting node, and then I need to be able to give it an offset. So let's say we want to go north and check that one first. So I've got already some predefined things for step north, but I could actually just make this a get node, and I could say get node and your grid position plus that. So neighbor is equal to that. So that's going to be another function we set up here. So a public Pathdata node. So another get node, but this one takes in a vector3 int with a grid position. And I will just run the existing function here. It just means that we don't have too many areas where we're duplicating logic. Because we know we can provide gridpos.y, gridpos.x. Means it provides the same behavior of returning null if it's invalid. So it works out nicely. So, okay, well, for me to be able to build a connection to this node, that neighbor has to not be a boundary. And it has to also exist. So if neighbor is not equal to null and they are not a boundary, so neighbor is valid and not a boundary, then we might be able to connect to it. Now, I only want to stitch like to like. So water can connect to water. Walkable can connect to walkable. Water and walkable can't connect. And if something is impassable, we don't build any connections at all, save some space there. And we also don't connect unwalkable to anything else. So all I'm going to do then is check, okay, well, if neighbor is walkable and node is walkable, so that's one criteria, or if the neighbor is water and the node is water, then we can connect those two. And the way we connect them is we would say, okay, well, node dot neighbor flags are equal eneighbor flags north. So this is our key bit that we can put into a function. So I'm going to set up a function down here, void update neighbor flags. We'll provide the current node. We'll also provide the path data. And we also need to have a direction. So eneighbor flags, direction flag. I'll bring these onto another line, make it a little bit easier to read. And vector3 offset, which then what this will do is So we bring this logic back here that we already had. So current node gets swapped in for this. And it just updates those. And we could also do a check here. We could change this logic around a bit. If it's null, or if it's a boundary, then we return no neighbor, or it's a boundary, so do nothing. Just avoids this getting too deep hierarchy-wise. Keeps it a little bit neater and manageable. Also means then we can bring that kind of onto the same line. Makes it a little bit easier to view it. Both the same. Our direction flag then gets swapped into here, and our offset goes here. Because then what we have instead is this becomes update neighbor flags, node, path data, provide the particular one we're checking, and we also then have grid helpers, and then we duplicate this a whole bunch of times, because then we just go and check each individual one. So it's a little bit repetitious getting it all set up, but it's something that once we've got it there, we've got a nice robust setup for being able to build the data. And while I'm not building connections between land and water, we absolutely could if that was appropriate, and we could do that per each set. That's the nice thing with having this grouped into the configurations. It means we can set up different sets of path data for different characters. So the final thing once we've got these set up is we need to be able to visualize this. We need to know that this is working. So we're going to update our debug display with the gizmos to be able to show the edges. West and northwest. So it's good. We're building up all of the connections, setting the neighbor flags, that'll get populated. Final thing is updating the debug display. So what I'm going to do is I'm going to actually make this a little bit cleaner in terms of draw debug node. Just make it a little bit neater again, where we can then have void draw debug, and it takes in a path data node. That's good. That'll just do a return. So that will draw the node, and then we want to draw the edges. So we'd be able to be saying fnode.neighbors has flag eneighbor flag north, and gizmos draw line from the world pos to world pos plus a vector 3. And we'll say in this case, if it's north, it would be 0, 1, 0, 0, 1, 1. And all these I'm going to just draw in the same color. Actually, no, I can... Yeah, no, I will draw them in the same color so that they stand out against the rest. So we just again... And this is one of the things with this stuff, you end up with lots of very similar code, debug code, in particular for debug displays, things like that. It's often going to tend to look messy, and there is often going to be you'll look at it and want to make it super neat. It's often not worth the time. If it's causing a performance issue, absolutely. But if it's not, I would generally just leave it and just accept the fact that it's going to tend to be messier code and that's okay. it's allowed to be messier code. So southwest. And it's very easy to get hung up. And the reason I mention this is because it's very easy to get hung up on trying to make code, particular debug code, super neat and tidy, and that's not always a good use of your time. What's key is that it's functional, it provides the information you need, and it's not getting in your road. That's the main important things. So let's generate this now. That should give us our edges. And we can see we're not creating connections into unwalkable areas, which is good. Our water is all connected, but we'll notice where it goes into the terrain, it's not. So when it goes into from water to walkable areas, it's actually a seam there, which is good. It means something could be on the water, safely navigate around on that. Something could be on land, navigate around on that, which is great. I will check in two final things for a couple of controls for whether those debug displays show different things. Bool, debug, show node. Just because otherwise it's a lot of data we're drawing. Debug, show edges. This will just mean we can turn these off if we need to. So F, debug, nodes. And then we'll do the same here for the edges. Just means we're not going completely ridiculous with the amount of stuff we're displaying. We can make it that we're showing only the things we need. It's running, turn on the nodes, and that's looking pretty good. Check our file size, see how that's going. 18 meg, which is pretty good. So that's with all of the edges and that in there, and we can see, if we take a look at how it stores that, we'll see that it's much more efficient. Now, neighbor flags, we can see there's big chunks where there's none, which we'd expect, because there's going to be a lot of areas around the boundary, particularly which would be at the start there, where there's no connections. So we've got our path data. It's at a fixed resolution, and it's at a one-to-one resolution with the source data, and that's a good starting point for it, because we've solved the key problems of making sure that the data is being able to be saved efficiently, which is really important, because at original file size, a lot of version control hosting would actually reject that because it's over the size limit that you can have for a single file. So we've reduced that size significantly, which is great. We've made sure that things are lining up perfectly with the terrain, which is really important. That is something that is so easy to get wrong, and is one advantage of having very variable terrain and terrain that is not symmetrical. That's one of the big things I would suggest when you are setting up your path data. Please do not have a symmetrical environment, because you will not easily be able to tell if you've got stuff wrong registration-wise. So we've got it being generated, we've got things being classified as walkable, unwalkable, water, boundary, we've got connections being built. So we've got the key fundamentals, we know those are working, which means what we'll be doing next time is we will get this set up so that we can work at multiple different resolutions. So we're able to generate data where we change our node size, for example, to one of the other settings. That's something we'll get up and running next time. And then that's going to lead into us being able to start to set up our pathfinding algorithms. So it is a bunch of extra setup stuff that we've had to do, but I cannot underscore enough how important it is to have those debug displays, make sure you've got the stuff working, make sure it's saving efficiently before doing any of the rest of the things. It's far too easy to get things misaligned. We already saw that with the U and the V coordinates for grabbing slope limits, and also from when we were reloading the file back in, it was rotating things. So it's really easy to miss and really important. So we want to make sure that we do get these things nicely grounded, so we've got a good foundation. Thanks, folks. I really hope you found the video helpful. If you're looking for the code for the project, the link to that is in the description below. And that code, you're freely able to use any of the stuff that I've made in that for any of your own projects, commercial, non-commercial, you can freely use that. If you have found the video helpful, please do chuck in a like and subscribe. It really, really does help out. It's very much appreciated. If you've got questions, chuck in a comment below. And if you're looking for other ways to support the channel, I do have a Patreon, and the link to that's in the description below as well. Bye.